You know that feeling when your phone seems to read your mind, finishing your sentences before you even do? Or how a translation app can just get the nuance of a conversation almost instantly? Well, the secret behind that magic isn't really magic at all. It's a powerful kind of artificial memory. Today, we're going to pull back the curtain and see exactly how these memory machines work and how they learn to understand time. So let's start with a really simple idea. To understand a story, you have to process it in order, right? The words king and dethroned mean something completely different depending on which one comes first. If you just jumble them up, the meaning is gone. And that's the core challenge for AI. How do you teach a machine to follow a narrative, to understand that context is everything? A traditional network, what you see on the left, is fantastic for something like identifying a cat in a photo. It just looks at all the pixels at once, and their order doesn't really matter. But then look to the right. For something like language, the order of the words, that's the whole point. This needs a totally different kind of architecture, a network that can process information step by step, actually remembering what came before it. So how do we build a network that can handle a sequence? The solution is as elegant as it is powerful. You give it a memory. It's not just about processing information anymore. It's about holding on to it, creating this running sense of context. And that, right there, is the core idea behind these incredible networks that can remember. No, okay, that's the official definition of a recurrent neural network, or RNN. I know, it sounds a little academic, but the key bits are processing sequential data and temporal dynamic behavior. Put simply, it's a network built from the ground up to understand that for some problems, time and order aren't just details, they're the entire story. This quote from Denny Britz just nails it. The word recurrent simply means the network does the same thing over and over and over again, once for each word in a sentence or each note in a piece of music. And the crucial part is, as it moves along, it carries this memory of everything it's already seen. But how does this memory actually work? Well, it's through a really simple, clever trick, a feedback loop. Think of it like an echo. The network processes an input and makes an output, but a little piece of that information, an echo of what it just did, gets fed right back into itself. That echo influences the very next step, and that's what allows information to persist and build up over time. And here is the aha moment. When we take that compact little loop and we unroll it through time, it stops being this confusing thing and becomes a beautiful, logical chain. Each link in that chain is a moment in time, a single word. It takes in the current word, plus the memory from the link right before it, to make its decision. It's a direct connection from the past right into the present. So this memory we keep mentioning, it has a technical name, the hidden state. But honestly, the best analogy is that it's the network's consciousness, its running summary of the story so far. With every single new word it reads, it updates this hidden state, packing in new details while still holding on to the context from everything that came before. But this simple form of memory has a critical flaw, a really big one, actually, one that almost made these networks useless for complex tasks. See, just like us, a basic RNN can be pretty forgetful, especially over long stretches, and this leads to a massive hurdle known as the fading memory problem. Just look at this sentence. To correctly predict that last word French, the network absolutely has to remember the word France from the very beginning of the sentence. The phrase, "I speak fluent," tells it a language is coming, but only that specific context of France tells it which language. This is what we call a long-term dependency. So what happens when that gap gets really long? What if the key piece of context was mentioned pages ago in a book? For a simple RNN, the memory of that early, crucial information starts to fade. It gets diluted with every new word it processes until it's barely even a whisper. The technical name for this is the vanishing gradient problem, but you can forget the jargon. Just imagine a game of telephone. The first person whispers a secret, but by the time it gets to the end of the line, the message is either completely garbled or totally forgotten. That is exactly what happens to the memory in a simple RNN. The original context just vanishes. So, how do we fix this fading memory? We need a more sophisticated system, one that doesn't just remember, but can actively decide what's important to keep and what's safe to forget. We need to build a smarter memory. And that's where our next big idea comes in. And that brings us to the hero of our story, the Long Short-Term Memory Network, or LSTM. And you know, these were invented way back in 1997 by Hotreiter and Schmidlber, and they were created for one single, focused purpose: to defeat this exact problem of long-term dependencies and preserve memory over huge distances. The secret weapon of the LSTM is something called the cell state. And the best way to visualize it is as an express information highway, like a conveyor belt that runs parallel to the main processing chain. Crucial information, like the fact that our story is set in France, can be placed on this conveyor belt and travel all the way to the end, totally protected and unchanged. So this memory conveyor belt is controlled by a series of gates. First, you've got a forget gate. It looks at new information and decides if anything on the belt is now irrelevant and can just be thrown away. Next, an input gate decides what new information is important enough to add to the belt. And finally, an output gate looks at everything on the belt and decides what part of that memory is actually useful for the task at hand. It's a totally ingenious control system for memory. Now, this isn't just theory locked away in some lab. This ability for machines to remember and process sequences is a technology that is all around you every single day. Let's take a look at where these powerful networks actually show up. Seriously, every single time you use Google Translate, you're using these ideas. When you talk to your voice assistant, an RNN is making sense of the sequence of your words. This tech is automatically writing captions for videos, it's analyzing the sentiment of a tweet, and it's even helping self-driving cars predict where a person is about to walk. Its impact is absolutely massive. If you look at the bigger picture of AI, LSTMs were invented back in '97, but they truly dominated the 2010s as the definitive solution for sequence problems. Since then, newer architectures like the Transformer have come along, the models that power things like ChatGPT. They can look at all the words in a sentence at once, not just in order, which lets them handle even longer dependencies. But they stand directly on the shoulders of the fundamental concepts perfected in these memory networks. And that leaves us with a pretty provocative final thought. We've successfully taught machines to remember our past and to understand our stories. As they get better and better at this, will they start to anticipate our needs, our desires, maybe even our next great idea before we've even had it?